Welcome to EDU World Space.
Let's find the values of x for which this series converges. And for those values of x for which it does converge, we'll actually find the sum of the series. So there's two parts here. So for part one, let's first find out when this thing will converge. So here I can rewrite this sum. This is actually geometric series here because you can pull out the n. All I'm using here is the fact that ABN equals ANBN. So I'm going from this direction to that direction, so I pull out the exponent, and then I see that this is geometric. And I can see that the r is negative 5x. And I know that geometric will converge if the absolute value of r, so in our case, the absolute value of negative 5x, or just 5 absolute value of x, is less than 1. So we need the condition absolute value r strictly less than 1, not equal to 1. And this is precisely why I use this inequality at the very end to set it less than 1. So solve that for x by dividing both sides by 5. And if you want, you could go ahead and use the definition of the absolute value to rewrite this as an inequality. So these are the values of x for which this geometric series will converge. So that's the first part of the question. So let me try to save some space here. So that's part one. Now for part two, using for those values of x, so the ones that we got in part one, the ones in which it actually converges. Now we assume x is between negative 1 over 5 and 1 over 5. And now, since it converges, let's find what the sum of the series is. So we know for geometric, the sum will equal, it's always the first term of the series. So this formula works regardless of what the starting point for n is, over 1 minus r. So in this problem, the first term of the series comes from plugging in n equals 1. So we have a negative 5x to the 1 power up top over 1 minus r, but r was negative 5x. So we just have negative 5x in the numerator, and then 1 plus 5x in the denominator. That's our final answer. So the series converges for these values of x over here, and for any of those values of x, the sum of the entire series is given by this expression over here in part 2.